So I wanted to do that as informal as possible in the sense that please interrupt me if you want. I was thinking that my previous meeting when I came earlier this year, there were like 8 people. So I thought more or less when I opened the door and said, oh my God, this is too much for me now. So if you think that there is, any questions, any feedback, I prefer that it's more interactive, okay? But let me introduce myself. So my name is Marcos Fernandez, and this is my 3rd year, just to put things into perspective, as an assistant professor in the Department of Space Studies, okay? So in my portfolio, I have courses on propulsion. I'm giving one on nuclear propulsion this semester. Next semester will be electric and rocket propulsion systems, which is part of that lecture. And then I have also electric, nuclear, rocket, hypersonics. I'm offering a course, air breathing engines, for the undergrad aerospace engineering program in mechanical engineering. And then I have a 6th one in the oven, which probably will be aerospace structures, mechanical structures, like docking systems, deployment of solar panels, and this kind of stuff, okay? What I love saying, and it's true that for me, I'm learning as much as you, so if you have questions, we can start dialogue and everything I'll tell you, 17 slides, so it's not very long, but at the same time, I'd like to talk between the slides more than show you many sentences and words and everything. Before that, I asked permission because as Dr. Young told me, which by the way, thank you very much for being here. It's imposing also. But before that, I wanted to share with you, we just came yesterday from the Tripoli event, Balls 32. Do you know what that is? Or does everybody knows what I'm talking about? A rocket event launch, which happens in Nevada, Black Rock Desert. It's 5 miles north of the Burning Man. You have heard of that also. There were some people coming from there. They finished apparently 2 weeks ago. So it's not a competition, as I already were talking, I think, about competition for rockets and everything. That's not a competition. You go there and you launch. It's organized by Tripoli, which is the other rocketry association, aside from NAR. And I went with one student. This is my 2nd year. We flew for L2, and he got it. My fin broke in the end, but when it touched ground, but it flew very well. And we were very happy to be there. I really encourage you. Yes, Tom, were you going to ask something? Sorry. I really encourage you, if you have the possibility, to participate in these events, because people are very nice, and there's 3 days. The landscape is amazing. It's on a bedrock, as you may imagine, in Nevada. And there are a lot of things that you learn. We are planning to go next year. So if anybody will be, I know it's early, but if anybody is, or soon, but if anybody's interested in that, let me know through Christian or something, because we would love to have as many people as possible, okay? So having said that, liquid chemical propulsion for rockets. So the idea of that presentation, as I had in mind, is that I know that you are starting a project on liquid propulsion, and that is great. And the other thing I heard, that I know that you have been working for several years in solid propulsion. And I say, okay, let's move forward to liquid propulsion. And that's the first thing I wanted to talk about, what this move forward means. So my question to you then, why are you moving to liquid propulsion? It's just to start a dialogue. There's not a hidden question.
You got money.
You got money, that's one thing. But from a technical perspective, which is what I was thinking, liquid propulsion, yes. Why liquid propulsion? So I wanted to put a couple of figures here. The RS-25, which is, as you know, the evolution of the engine that was used in the shuttle, the thrust-to-weight ratio, if you evaluate that, is 73. The case of the shuttle SRB, it's 16. It's a much heavier rocket. However, except for SpaceX, I would say, because I heard from them that they want to get away from solid propellants, we are still considering solid, because solid will give more thrust in the end. However, as you can see, if you divide by the weight that you have, the thrust is much more interesting in the case of liquid propulsion. So that could be one of the idea to say, okay, we want to move forward because in the end we are going to have an engine which is going to give us more thrust per unit weight. The other thing is the specific impulse. As you can see, only the RS-25, and this is not a huge figure. It gives like 366 at sea level. Do you all know what the specific impulse is, by the way? No. Okay. So there are some. When we start thinking about what we want for the rocket, basically what we want is to push it forward and go up, right? So there are two things to do when we have a limited amount of energy, basically, which is to push something which is very heavy and it will not going to be pushed very much forward, or something which is lighter, which we will be able to push forward, but it's lighter. So in the end, that comes down to what is a propellant, right? So if you're using something very light like hydrogen, you would be able to push it very fast because hydrogen, as you know, is the lightest element. If you go to for example, RP1, which is a derivative of kerosene, it's much heavier. You won't be able to push it as farther, okay? So specific impulse, basically, without going into too much technicality, would be able to evaluate to balance these things. For engines that are working with hydrogen, 366, they are pretty higher values. As we are start getting molecules in the chemicals which are heavier, we are start bringing down a bit this value. As you can see, it's counted in seconds. Now, if you are all engineers, I can tell you that basically, if you take the thrust and you divide by the mass flow, which is the amount of kilos per second that you are delivering, you will get that figure. Roughly speaking, if you multiply by 10, you would have more or less the exit velocity through the nozzle. Nozzle like that. It's not exactly that, but it's an idea, suggest what will be the velocity you will get here. So in other terms, the higher the specific impulse, the better. You know, by the third Newton's law. So if we have a velocity or a momentum going in one direction, we'll have the momentum going in the other. So in that sense, it's good to have higher values here. I can tell you also that maximum that we can get is the energy that we can have in a chemical reaction, right? So maximum values, I will say about 460 seconds, and it will be very difficult to go much farther than that if ever we can. Okay, if you go beyond that, we have to start thinking of other systems like nuclear propulsion, or even beyond that, we will talk about electric thruster. However, take into account that in all propulsion, there is a balance between thrust and a specific impulse. So if we are having high thrust here, lower specific impulse, if you go to higher specific impulse, using, for example, nuclear and electric, as I said, you will have less thrust. In other words, chemical propulsion is the only means we have to escape Earth. Because as you know, we need on the ground more or less 11 meters per second. And that's something that we cannot avoid, okay? Questions so far? Okay, so liquid chemical propulsion history. Who has heard about Tsiolkovsky? Okay, some people there in the back. Normally, the people who are in the back are the ones who, I mean, in my days of high school, are the ones who knew less, but here I see it's the contrary, so it's okay. They are in the front. They are in the front on the other side. I am the one who's in the back. That works now. Thank you. No, yeah. So Tsiolkovsky was deaf. He was Russian, and he was thinking a lot about how to bring rockets into space. I think it was in 1906 or 1904. My memory is not what it used to be, but in any case, he wrote an equation which remained in history like the rocket equation, the equation that we can use to know how much propellant we need to give an impulse, change in velocities, or if you want delta V, at a specific with a specific impulse. Okay. Interestingly, there have been other engineers or scientists or thinkers, if you want, who reached the same conclusion without apparently knowing his results, because Tsiolkovsky was a bit away from the intelligentsia in those years in Russia. So basically, it's not that his works were published as soon as he finished them. They took a lot of time to get to be known and everything. But he remains historically one of the first figures. To think about that. It's interesting to say that space travels are possible with cryo. Cryogenics means hydrogen and oxygen. I was talking on hydrogen before. there's an obvious advantage, which is hydrogen is very light. Put the two things together, hydrogen and oxygen, and you are going to have reactions, products, for example, water, which is not very heavy. So you would be able to expel at high velocities. Okay, this is what cryo means. However, we talk about cryo, so we have a problem here. Does anybody know what the problem is managing cryo?
It has to stay cold.
It has to stay cold. And what is when we say cold? We say liquid. You know which more or less the temperature of liquid hydrogen?
200 degrees below 0 Celsius.
Yes, more or less. I have like mine 20, 30. It depends on the pressure, but yes, Kelvin. So that means that we need tanks that first, hydrogen is so light that it occupies a lot of space. Same mass is going to be because the density is low. On the other hand, we have to keep it at very high pressures to keep it liquid so that we can concentrate more hydrogen. That means that the tanks in the end are going to be thicker. That means it's going to be heavier. In the end, what you have to keep in mind is that engines is not the excuse why we are going to space, right? Because the reasons can be political, can be military, can be scientists, but never to test a rocket if you want. The rocket is what is going to help us. So what I say that is that rockets, what I'm bringing up is what we call payload. If we have a rocket engine, which is very heavy, the payload mass goes down. So that means that in the end, the cost of the travel will be higher because we'll have to charge more for a lower payload to go up. And that's a problem. So things to take into account. Goddard here, he started with gasoline because obviously it's much easier to handle than hydrogen. But curiously, he was using a low oxygen to fuel ratio. Now, without going into details, you may imagine that there's an ideal relationship between the oxygen, oxidizer, and the fuel on which we have maximum efficiencies, specific impulse if you want. He was using low O2F ratio. Okay, so a lot of gasoline, basically. There are other people we can talk about, like Oberth. He was from Romania. He published a book in 1923, the name of which I have it in my notes, but I don't have it here. It's not a problem. It was something like Space Travels, and he was one of the first theoreticians on space travels and propulsion. Okay, his book, by the way, got a second edition in 1929, if I remember correctly, and that's the book that von Braun read, and he became very much passionate about space. And I don't have to introduce von Braun, right? So we all know who he was, the programs he did. This summer, I offered a book club in my department to my students, and it was a biography of von Braun. He is an interesting character because he was working for the Nazis. He's from Germany in the 30s, and then in the 45, when the war finished, they moved back here. But he had a very interesting life, let's say that, because they had to escape the Russians. They were falling in the Russian side in Germany when Germany was falling in 1945. The Second World War was finishing. They brought him here through Operation Paperclip, so it was good. Snow Peltery, it's another figure. He was French. And then we have Fritz Lang. Fritz Lang was not an engineer. He was a movie director. He was from Austria. He became American citizen eventually, and he made this movie, Frau im Mond, on which, by the way, obviously it's the woman in the moon. Von Braun participated as a consultant for the space aspects of that. They wanted to make something very similar to what would be to fly in space. Moving forward, we have Galsit here, which is the Guggenheim Aerospace Lab of California, Institute of Technology. In those times, the director or one of the main figures working there was von Karman, Hungarian, also came here in the 1920s, not because of the Second World War, to look for further opportunities. He was working with Planck. You remember that name in Germany, but he didn't seem to have much opportunities. He decided to move here, and he found, he also wrote a book called The Wind and Beyond, which is very interesting. So he helped a lot of projects in space in California in those times, and we are talking 1940s. They were trying this mixture, methanol and NTO. If I am correct, Tim, I think you told me that you were going to try ethanol and nitrous oxide, correct? So this is different, but it's also an alcohol, and they were using N2O4, which is more powerful, but also more dangerous. So one of the projects they got with JATO, it stands by jet assisted takeoff. So it's basically to take an aircraft and put a rocket behind so that you are going to have a very short runway to take off. As crazy as it seems, it worked. And eventually, that was, if I remember correctly, one of the first projects that offered them the possibility to work with the Department of Defense, and they started the JPL, Jet Propulsion Lab, which eventually became part of NASA. Okay? Many interesting people working there. There was a group of engineers and crazy people who wouldn't doubt to work in a very unsafe manner, I would say, with liquid propellants. There was this guy called, have you read the book Strange Angel? Parsons, that's his name. So Jack Parsons, if you have the opportunity, that's another very good book, very interesting. It's about setting the ambience of California in those years, and there were many. He was part of the occultist, a dark cult or something. I mean, there's something very interesting about that figure. Unfortunately, he died when one of his propellants exploded. He was mixing things in a very unsafe way. They fell on the floor, and there was a big explosion. In Germany, some years before, they started with hypergolics. So what is that? Anybody? Yes?
It's when two chemicals will combust immediately when they come in contact with each other.
Exactly. So two advantages of that. First of it is that they are very powerful. Second, you don't need a match. They are going, as soon as they come together, they explode. So you have already the energy that you need to have propulsion. In that case, the hypergolics were BMW, the same trade as the cars. They were the ones who started investigating this mixture. By the way, speaking of hypergolics, it became so difficult to handle because of that. As soon as they came into contact, they exploded. That these ideas were developed, but they more or less they stopped for a while, and they have been recovered lately when more safety measures have made them more interesting to work with, basically. Okay, and then we have SpaceX, and they have been betting on liquid natural gas or liquid methane. Do you know why? Yes, let me ask him because
Efficiency.
Efficiency and what do you think is easy to get? Yes, but
it is easy to make on Mars.
That's it. So SpaceX wants to go to Mars, and they said, if we go to Mars and we carry half of the propellant, we can make the liquid natural gas or liquid methane there and bring it back on the way back. That means that we can double basically the payload that we would be able to carry. So that was the interesting thing that they have, and that's why the bigger rockets they have, they are not using solids. Don't talk to them about solid propulsion. They don't want to hear about that. So they are going to go for liquid natural gas or liquid methane. Okay, liquid methane is still cryo in the sense that we have to lower the temperature a lot to keep it liquid, but not as low as hydrogen. So it's easier. Okay, it's also heavier. Questions or thoughts or ideas? Okay. So what I'm going to do now is to go part by part. I'm going to explain a bit the ideas that's, and I prepared this presentation thinking of you, thinking of which ideas from an engineering perspective could be interesting to explore if you want. Okay, just throw it there. So the storage tank is the first thing. One of the things we said is that it's interesting to have a light propellant. Normally light propellants are less dense, which means tanks are bigger. So we will need, first of it, is that tanks can have to be thicker to keep the high pressure, to keep them liquid, and that is a problem. So we have to find the balance there. Another thing there, the problem is that once we are in space, as you may imagine, we have no gravity, right? So somebody was telling me in class in nuclear propulsion today, I mean, it's like you could here you take a bottle of water and you put it upside down and all the water flows down. When you are in space, the water or the liquid you have is going to float inside of the tank. It doesn't mean it's going to go down. Unless you have some system which is going to propel the rocket forward or the engine forward, and because of the acceleration, the liquid comes back and it starts the process going through the engine. But there are things that we have to avoid. One of them, apart from that, is the gas pressurization, which are two systems. As I said, we have to keep high pressures inside. How to do that? One of them is an exogenous system, which is basically using an inert gas, something which is not going to react with hydrogen and oxygen. Obviously, we add it there, like for example, helium or nitrogen. I think your project is going to work with inert gas to add pressure in the tank.
Yep. Yeah.
Correct?
Nitrogen.
Nitrogen.
Kind of what we're thinking.
Much easier to work than helium. I think it's cheaper, and we have a lot of. So the idea is, obviously, the condition is that whatever the gas you are going to use, you have to avoid it to react inside of the tank. Nitrogen is an inert gas, so that will work great. Autogenous alternatives, on the contrary, the way they work is that since liquids, in any case, hydrogen, if it starts warming up a bit, starts to evaporate, is the same gas of hydrogen, which is going to provide the pressure to the rest of the tank, if you know what I mean. The thing with that is that you have to use part of the hydrogen to self-pressurize itself inside of the tank, and you will have it in gas form. But it's another system which is sometimes used in bigger tanks, in bigger engines, but it doesn't mean that exogenous is also used. Okay, I think, if I'm correct, the RL10, it's using exogenous with helium. And sloshing systems. Now, we are going up, there is a lot of vibrations. These things are huge. So what happens is that you have a sloshing inside of the tanks. This sloshing can unbalance the rocket, and we want to avoid that as much as possible. In other words, speaking from in engineering words, we have to absorb part of the energy that is being generated because of the movement of the tanks. A Danish company, and that's not new from them, it's just a design that they did, but that concept has existed before. They add, as you can see, some kind of tabs inside of the walls of the tank, so that whenever the liquid is moving, these tabs are flexible and they absorb part of that movement. So they reduce the chances of having slosh. Okay? So there are things with that. Moving forward, the turbopump system. That could be part of the whole week, and we are not going to spend there. One of the first things that I asked Dr. Young is that if you were going to work with turbopumps, apparently not. It's a good idea because turbopumps are a project in themselves. They are complicated, but they are very interesting also. It's a way, instead of using a gas to push the liquid outside or the propellant outside of the tank, it's a way to add pressure to the liquids that are, to the propellants and the oxidizers that are coming out from the tank before they enter the combustion chamber. Okay. So turbopumps, normally it's turbine and a pump. So a turbine, what it does is it moves through a hot gas and it transmits that movement to the pump, which increases the pressure. The interesting thing here is that the gas is generated by the propellant itself. Okay, and there are several ways to do that. We are not going to enter there. You can use a small chamber to pre-burn a bit the gas so that you already have gas to move the turbine, and the turbine through a gear. You can see the gear in the middle. It will move the pump, which in this case, if I am correct, is at the top of that picture. The turbine is at the bottom. Okay. There are a lot of things to talk about that. I don't want to, but one of the ideas that comes to my mind is the problem of cavitation. So do you know what that is? What is cavitation? Anybody? Yes.
It's like when main propeller spins, it creates pockets of air behind it.
Exactly. So you know what vapor pressure is. We have a liquid. If the pressure goes below a certain level, we start having bubbles inside of that liquid. That's bad because that bubbles eventually, when they reach another area where they are higher pressure, they collapse. And that collapse, they generate sonic waves inside of the liquid that eventually can damage whichever part they are touching. In this case, what typically happens are in the pumps. In order to avoid that, the big pumps, what they have is that is an impeller, which is a part which is the purpose of which is not that much to increase the pressure at the end of the propellant, but just to avoid the possibilities, the chances of having cavitation. Cavitation exists not only in turbopumps for rockets, but if you look, for example, in propellers for submarines, you will see that there are very cool videos, by the way, about that in YouTube, that they generate a stream, a jet of bubbles and they collapse. And eventually, if they collapse in the propeller, in the case of submarines or in the pump moving parts, they end up damaging it. So we can have an accident, basically. Okay. Questions? Nothing? These things are very cool and complicated. So the manifold. So now we have the turbo pump, and basically we want to transfer everything through a manifold to pipes and towards the combustion chamber. So obviously, what are we going to ask about that? Is non-reactive metals. We are having liquids, which in the case of cryogenics, they are very cold. So one thing is the temperature. The other thing is that depending on these propellants we are using, eventually we are going to have a reaction with the material that manifolds are made of, and we want to avoid that. Normally, or materials or alloys that I have seen are Inconel, typically nickel, aluminum. They are typical materials where the manifold is made of. These are all these tubes that you can see in the. I had it here, but it has broke down on the motors. Okay. Pogo oscillation, another problem that might propagate there. What is that? It was a very serious problem on the first rockets. They didn't expect that problem to happen. So when we'll see later that the combustion happens in the combustion chamber. The combustion can be something that can be very, balanced, or they can be instabilities there, right? When there are instabilities, that means that the thrust is not going to be like that, like a straight line. Is going to go up and down all the time. So what happens is that the rocket starts doing that. But when it starts doing that, oscillating vertically, what happens is that the liquid inside of the manifold starts doing the same. So we might risk end up breaking because of the reaction of the liquid movement, the mechanics of that on the manifold, breaking the engine also. Okay, these oscillations can also, without being that dangerous, can also be very uncomfortable for the crew members. So we want to reduce that as much as possible. Normally, the good thing is that Pogo oscillation was easy. Once they was detected, it was easy to control, and the frequencies are not that high. We are talking about tens maximum of hertz. Okay. And then the flexibility, obviously, because as I'm saying, if there are vibrations, we will need systems to absorb that. And as you know, the best way to absorb vibrations is to have a flexible system, something that is going to be able to come back to equilibrium without breaking. Okay. Questions? Okay. So, cooling system. Question to you. I don't know that. Are you foreseeing for your project any cooling system?
Most likely needing regenerative cooling for sustained burns.
Okay, that's great. By the way, I have to tell you that I'm very curious about I would love to see how it works and everything. Okay, because I think it's great, the idea you have. So normally, cooling system, what happens is that if you take the temperature of the gases that we generate in the combustion chamber, or that the ones that go through the nozzle, and you see what are the limits of the elements, the material that you are using to build up the nozzle or the combustion chamber, you see there's something that doesn't match here because the materials would melt. In order to avoid that, we need something to cool down the system. So basically 3 ways to do that. Very basically, radiation cooled. There are materials which radiate to the outside, especially in the nozzle, which is facing the vacuum of a space, part of that excess heat, okay, so that we are not going to concentrate that there, and or at least for us up to a certain amount of time, it's going to work. Radiation, you know what it is. I mean, I don't have to explain that. Regenerative cooled, basically, and this idea is not new. Even Goddard, if you look at his first sketches and his first experiments, he was introducing that. So basically, you take the nozzle and you add to the sides of that tubes where you are going to have the propellant, which is cold, through it. What happens is that the propellant is in contact with the walls of the nozzle. They absorb part of that heat through conduction. It comes through the propellant. The propellant becomes gas, and now it would be able to move the turbine. So it's a system that fits itself. There are a lot of advantages of using regenerative cooling. That one, I found it very interesting. And by the way, speaking of which, I wanted to say something else. It was a news in the last week. RL10, the Aerojet Rocketdyne engine that has been flying for, I think, 60 years. There is a new version that they are developing now. These tubes normally, they were very difficult to do because you have to integrate everything in the nozzle shape, for example, in the combustion chamber. So they were soldered there or brazed. The problem with soldering is that you cannot make a perfect solder, and there might be problems in the thermal conduction there. So they started doing it using 3D printing, which is very interesting. Speaking, I had lunch with Dr. Yang last week, and he was telling me, and something I had not thought about, and it's very important also. When you have, problem is that when you have dust or very small particles of metal mixed with the propellant, that's not a good idea, right? Because you might have an explosion. So when you do that in 3D printing, one of the ways they have to do that is that you put on a surface these small particles of metal, and you start melting them with a laser, and you start going up with that. Chances are that you are going to have remains of this raw material inside of the tubes. So the way RL10 is solving that is that, as you can see, the nozzle with the combustion chamber, they have a throat, a minimum area. They cut it here, they do one part and they do the other, and then they solder it together. But the reason to do that is that they have more access to the tubes when they are two parts, and they are more able to eliminate any minimum particle that has stayed there. Okay. A transpiration cool, as you can see, is just a system like a kind of a foam made of metal. I have it here. They are used. There is a company called Ultramed that are using iridium, rhenium, and or a ceramic matrix here, and they are able to absorb part of the hydrogen that is running there, and they transpire through the walls. And this liquid hydrogen, it makes a film. It makes a film through the nozzle, which protects it from the hot gases. Okay. Another system obviously used when you are ready to lose a bit of propellant. In that sense, I don't think it could be applied to big rockets or rocket engines, but it could work in the small designs as well. It's interesting. The combustion chamber, where the action happens. So first of it, we have injectors, which is what I have put here. There are a lot of things that we can talk about that. Basically, turbulence. We want a turbulent system inside instead of a laminar flow. The reason for that is that when we have turbulence, the distribution of heat is more homogeneous, and then the mixing, or let's say the other way around. First, we have to mix propellant and oxidizer, and then we have because of the reaction, we have a heat generated that has to be distributed as homogeneously as possible. So with turbulence, we can achieve that. Now, as you can see, injectors are the system that are going to inject, in fact, the propellant and the oxidizer inside of the chamber. And there has been an evolution from the F1, from Saturn V through, you see the pintle injector here and the quartz swirler. How does that work? Basically, the thing that I wanted to highlight here, you see that this is on the top of the combustion chamber, and you have the same small holes. These holes normally are not straight, could be, but they realize that if you have jets that are impinging on each other, like fuel and oxidizer, you're starting having the mixture. So that's interesting. Now, if these holes are done in an angle so that the oxidizer and the fuel, they meet too close to the injector, the heat stress that the injector is going to resist, it will be too high for them first. So they try to be a bit far away from that, which unfortunately might make the combustion chamber a bit longer. And then the other problem is that these lines, you know what that is for, these veins, they are trying to break the homogeneity of the explosion to prevent this. One of the problems they have in F1 is that they have very high frequencies detected in the combustion chamber through the combustion process that might end up breaking the engine, because contrary to the pole, these oscillations can be very high frequency. And when I say high frequency, I'm talking about thousands of hertz. So what happens here is that these veins were designed so that they broke the flame front, basically, and they broke the resonance that the explosion, the combustion process might have with the combustion chamber dimensions. Okay. Vibration. Now, other systems that have been used are pintle injectors, for example, which are basically, they are cylinders, tubes, where the mixture sometimes it happens inside the pintle injector. It's a hydrodynamic system where you can open and close the valve on the bottom of it, and you will have more or less propellant inside of the chamber. In other words, we are controlling the thrust through that. And the coax swirler, basically you have, and you can see here in the picture, you have, for example, the oxidizer here, and you have the fuel outside. The fuel comes in a kind of a cone. The oxidizer comes inside. Eventually, the small droplets of oxidizer and the cone of the propellant, they mix. They break the structure and the mixture, thanks to the mixture process, the combustion starts, okay? Questions? Yes.
What is the benefit of the coax swirler design when it comes to it being like, I guess it appears to be a very delayed mixture of the oxidizer and the pellet?
What would you think, or anybody?
So I'm trying.
No, if you're, yes, but I mean, it's a very fair question, but
Just makes a homogeneous mixture in the end.
yes. These parts, the coax swirler, are not in the combustion chamber itself, are just outside. So it's the jet which is entering there. When you say it's taking more time, in the end, in fact, it's not, because by the time they enter the combustion chamber, the mixing process, it occurs quite fast. And the reason for that is that you are maximizing the mixture process. You are making it more efficient, basically. If you separate in the combustion chamber the fuel and the oxidizer, this is like being in a party trying to find a friend who's on the other side of the room. So it will take you a while, especially if there are many people. So in this case, you are trying to bring everything together. When it's the appropriate thermodynamic conditions, temperature and pressure, the combustion ignites. Okay? Especially if you already have the flame right there. Okay. Another question? Sorry. So 3 examples of nozzles. As you can see, the nozzles are huge parts, and the ones that normally we see and we think of an engine, we think of them. The first of them is the BP4 engine, which works on liquid methane. Just the Raptor from SpaceX, the same, and the Merlin 1D, that one, it works with RP1, which is, as I said, RP stands for rocket propellant, and it's a refined kerosene. Not much to say because that has a lot of theory, but basically, as you can see, they don't have normally a straight shape like this one. They have more a bell shape, and it's a shape that has been optimized so that the expansion of the gases, what happens, by the way, the gases that run through the nozzle are, ideally, they are supersonic. So what happens when you have a supersonic flow and you increase the area? The velocity goes up, right? And the pressure goes down. So velocity and pressure always go in different directions. So velocity goes up, that means that in the end you end up having more specific impulse. That's what we want, okay? Obviously, there is another factor here. I'm not going to enter into details, but as you may imagine, this velocity will depend on the background pressure we are having. As you may imagine, here at sea level, or more or less at sea level, we are having maximum pressure. As we go up, the pressure goes down. So that means that the specific impulse increases as we are going up. Okay, that means that when we were talking about specific impulse before, we have to say, what are you talking about, sea level or vacuum? It's not the same. In vacuum, there is no resistance for the gas to leave the nozzle, right? There's no pressure, there's no air, there's nothing. Here, yes. Okay, without entering into detail, but there are things to. So, things that I wanted just to throw at the end of this presentation, some ideas into in here to say they are research that we are interested, but we are just starting, and just to say that there are things that will be cool to think about. We talk about the combustion chamber, the atomization, to make the droplets as small as possible, to maximize also the mixing, the vaporization. I mean, the smaller the droplet, the easier it's going to be to become gas. When it's gas, it's much easier to start the combustion process. Diffusion of the droplets inside of the combustion chamber. Turbulent versus laminar, heat transfer, how the heat is transferred between within the combustion chamber towards the walls. What can we do to protect the walls? Sometimes the walls inside of the combustion chamber, they have film cooling, which is film propellant itself, which is being dropped through the walls, and the energy that takes to vaporize that propellant will not reach the walls themselves. So we are protecting the walls, basically. Okay. Instabilities like screeching, which is the high frequency instabilities I was talking about before. If you like CFD, I'm not an expert there, but I tell you that there are many things to do. That came from a study, and they were analyzing what is the droplet mixing process, liquid droplet breakup between supersonic and subsonic conditions. And it's not that I wanted to go there into details because I don't know them, but basically it's to tell you that CFD, as you may imagine, techniques are very much applied here. Another possibility is to analyze the stresses, okay? Nozzles are big structures. They are going very fast. Thermodynamic stress also adds to the mechanical stress. Are we going to be able to resist all that energy there? So we can do simulations in ANSYS or something to see whether different materials would work or not. Obviously, the idea is to optimize that. By that, I mean that there are areas which will have maximum stress. For example, for temperatures, the maximum temperature is here. The throat has the minimum area, and there is a lot of friction there. There's a lot of temperature. There's a lot of heat transfer in a small area. We have to reinforce that area. Reinforcing that is less important. So it is, but it's less. So we can do that, okay? And then after that, well, I just put that green monopropellants because they are, without going into too much detail, monopropellants, do you know what they are? You want to share? And you want to? I'm sharing. Mono means single, right? So in that case, it's a bachelor. It means that instead of having oxidizer and fuel, we just have one propellant, which is being decomposed using catalysis effect. The decomposition of a propellant will release energy also. In general, that energy is lower than B propellants because it's not a reaction as we have it's a reaction, but it's just the composition. However, in the small satellites where it's much more complicated to deal with two tanks and everything, sometimes monopropellants are used. An example of that is hydrazine, and which can also be a hypergolic. You can use a catalytic bed. You make it cross. I don't know what the material is made of, these beds, but they react in the contact with certain metals, certain elements, and they decompose and they heat up. And then we can have also propulsion because of that. The new research, new trends, that picture is interesting because many, for example, hydrogen is, I mean, it's dangerous if we inhale it. The DOD has been investigating some new monopropellants which are not poisonous. They are not going to be affecting us if we are going to work with them. That's why the researcher there is not using a mask or anything. It's typically they used to when they were working with monopropellants. And to finish, I wanted to show you something that we have started making progress. So we have started talks with the Department of Atmospheric Science, which is just below us. We are in space, atmospheric science. It's in the 4th floor in my building, which is called Clifford. Yes, I forgot, sorry. So the idea, they are very interested in seeing the effect of the rockets in the stratosphere, okay? Rockets, two things there. One of them would be the exhaust of the rockets. The other is the ablative process, how when the satellites come down and they burn in the atmosphere when they came at the end of their operational life, that material might stay there in the form of aerosols and end up provoking some, for example, affect the ozone layers there. They are very interested in the part of the impact on the ozone layers, and obviously we were thinking of contributing also, bringing what will be the rocket exhaust that we could expect there. The good news, or the bad news for us, is that it's solid propellants normally, the ones which have metals inside like aluminum particles, which may affect more the ozone layers rather than liquid propellants, okay? But there are some compositions of, especially for hydrocarbons like RP1, soot particles that might stay there, and apparently it seems that it could affect the environment. It's very challenging, as you may imagine. How do we bring a probe there to try to measure if the models that we have here on the surface of the Earth, they are true? Are we going to use drones or balloons? Drones, they have a limit to fly. I mean, altitude I'm talking, and then maybe balloons or something. But then the other thing is, are we going to put a balloon next to a rocket when it passes to just to measure? There are challenges still, but just to let you know, there are things that we are thinking about. Human activity, well, that has to do more with the ablative process. Apparently, I took that from internet. So SpaceX last year they blew up rock engines in the high layers of the atmosphere. Recently, some researchers, I think from Russia, they have detected that this explosion created some instabilities in the ionosphere, a bit higher than the stratosphere. They made a hole, and they provoke apparently a lot of problems there that it will be interesting to analyze. That has to do with chemical reactions that happen there and everything. Okay. As I said, UAVs or balloons would be ideal to go there and see what are the effects of rockets are becoming more and more normal, right? So we are going to have more travel to space, we're going to have more traffic there. What is going to be the effect of all that? And to finish with that, I just wanted to show you our IBAPTIS, that our lab. We have a small room, SSPL, Space Studies Propulsion Lab. And that was last week. Yuri, the student I was talking to you about, he got L2. That was his rocket. And he started painting it as the V2 in black and white. And then he put these colors, red and gold. That's another of my students with a small 3D printer we have there. And I think you know that the Orion capsule, they came. And we are probably going to, the last news I have from Pablo is that they want to, because it doesn't fit in the, as you may imagine, in many buildings. So they are trying to put it outside of Clifford. They are trying to sandblast it now because it has been outside for a long time. It has never flown to space. They were using it just for tests, okay? But they wanted to clean everything as much as they could. In addition to that, as you know, we have the H1, the motor, one of the engines from Saturn 1B. That is being cleaned now. So everything very cool. And the last thing I wanted to share with you is that we have a blog, and you can find the link. I didn't bring it here, but you can find the link in my website at UND. You look for my name, UND, and there is, say, you can see the blog here. And we try to put news about what we are doing every week. Some news are funny, some news are more serious, but just to keep on the ball rolling, as I say, okay? I know it's 7. I still have a course, but I have time and I don't want to overburden you. So that's what I have for you.